Okay, good afternoon, everyone. Welcome to the course on quantum computing. So, as Gargi mentioned, we will be starting with a brief review of quantum mechanics. And then, after having revised quantum mechanics in the first, can we reduce the volume on this, please? Um, uh, After we revise the basics of quantum mechanics in the first week, then we will try to get to quantum computing. So we do have attendance and some quiz questions to keep you awake because I'm very well known to put people to sleep, especially on Zoom. So let's see. I'm going to launch the poll. And so please answer only the first question, which is please enter your full name for attendance. And please enter the name you used to register, or the name that you would like to the name that should appear on the certificate. Are you able to see the? Is everyone able to see the first quiz question? Okay, thank you. So let's get started with the course now that the attendance is done. So I'd like to begin with what quantum mechanics is. So it's a general theory that is applicable to all physical systems. Everything is ultimately quantum mechanical. But there are three essential features of quantum mechanics. That is, when people were doing experiments in early 1900s, there were these three essential features that were observed, which could not be explained using the models of physics that existed then. And these three essential features are: one is discreteness, the second one is diffraction, and the third one is coherence. We will see what those are. So discreteness meaning, as you can see here, the current through a mercury vapor, through a tube containing mercury vapor versus voltage. That is the plot that you are seeing here. And what was observed was that there are current peaks at certain voltages. And these voltages correspond to multiples of 4.9 electron volts. And so this sort of shows that the electronic levels in that mercury vapor are discrete. That is, they're going in multiples of 4.9 electron volts. So this is famously known as the Frank-Hertz experiment, which provides evidence of discrete atomic energy levels, which is the first essential feature of quantum mechanics, that energies levels are not continuous, but they are rather discrete. And these experiments have been done with modern precision. For example, as you can see here, in 1988 and even later on, people have resolved hydrogen states with much more clarity, and you can see that these states are very discrete. That is, they're not continuous energy. And so the discreteness of this atomic spectra, the first essential feature of quantum mechanics, is experimentally observed. So what we are trying to do when we talk about quantum mechanics is we are trying to look at experiments that cannot be explained using existing theories of classical mechanics or classical physics, and trying to develop a general framework to explain these. So the first of those features is discreteness in energy. And the second one is diffraction. Davison and Germer in 1927, they observed that if you have electrons that are hitting a nickel crystal surface, you can observe a diffraction pattern. Until then, basically, things like light were observed to show diffraction or interference. And as you know, the light is a wave, but electrons were considered particles. So electron diffraction was not expected. They were expected to behave like, for example, how tennis balls would behave, like particles. But so this diffraction was observed, and that was a very shocking observation that required different analysis compared to the classical models of physics. For example, here I put an image from my lab where we did electron diffraction on a single atomic sheet of graphene. And graphene is one atom thick carbon lattice, which has hexagonal pattern, and so you can see the hexagonal pattern here. These spots are actually coming from the electron diffraction. So this diffraction is a universal phenomena that you can observe with electrons and even molecules. Like, for example, using fullerene molecules, people have done experiments where we were able to observe diffraction. So particles are not expected to diffract like this from the classical physics models. So there is something new going on that required a new theory, new framework to explain. So as we have seen, two essential features, discreteness and diffraction. And then the third one is coherence. And so this is an experiment done by Hitachi, which makes electron microscopes. So what you have here is a source. The source is a tungsten filament. It could also be a lanthanum hexaboride filament, which is much better in terms of emitting electrons, but it doesn't matter which source you consider. This source is emitting electrons, and it is maintained in such a way that it is emitting one electron at a time. And what you have here is a divider, and so you have one slit here and one slit on this side. So it is like a double slit experiment. And so as the electrons come from the source, they either go this way to the left or to the right, and then they fall on the detector, and each detection appears as a localized particles. So we do have a video that I'm going to show, and you can take a look at that to see how this experiment proceeds. So here is the actual video of the Hitachi experiment that was recorded. So you see these detector planes, you see localized spots. As each electron is being emitted, it hits the detector at one particular spot, and electrons are being sent out occasionally based on the source, right? So you keep accumulating these spots, and this experiment is run for a long time. So I'd like to pause the video, and when you look at the screen here, you see that these localized spots, they pretty much appear randomly. There is no pattern to them. That is, electrons are being emitted from the filament and they're hitting the screen at some point, and so they appear to be random. But if we do this for a long time, let the electrons accumulate, so keep running this experiment for several hours, you still don't see any pattern, but as the electrons keep getting accumulated, a pattern begins to emerge. So as you see, slowly you can start to see bright and dark fringes as the pattern builds up. I also have some screenshots. If you are unable to see it properly, we can see the screenshots. Because this is a video that was recorded in 1980s, the thing may not be clear on Zoom. But now as we accumulate more and more electrons, you can begin to see the patterns here. So let's go back to the slides. So in the beginning, when only few electrons are emitted, you see single spots. As you keep accumulating, now you see here in panel D here, you can see, for example, if I look at this panel, you can see patterns emerge where you have bright and dark fringes, just like how we would expect in light. So this shows, this interference requires that the electrons that were emitted are coherent. That is, they have some sort of a coherence. And we will discuss what this coherence means in more detail later. But for now, we will just say that these electrons that were emitted from the source were coherent, and this coherence is the third essential feature that led to the development of quantum mechanics. So previously, people were observing, for example, in Young's double slit experiment with light, you would observe the same fringe pattern. And so then we could say that the particle is associated with some wave structure. We don't want to say that the particle is behaving both like particle and wave. That doesn't make sense. That is against your intuitive common sense. So we would say that the particle is associated with some wave structure. And what this wave structure is, we will see in more detail. So this wave structure that is associated with the particles it introduces the possibility of interference and the quantization of energy levels. So these three essential features, discreteness, diffraction, and coherence, are the three essential features for quantum mechanics. So quantum mechanics, as you have seen in this experiment, it's not dealing with individual particles, but it is only dealing with statistical results. So it is only dealing with ensembles, which are described statistically. So it should not be mistaken for single particle measurements. So let's begin with the postulates of quantum mechanics that we are using to that we are using to develop the theory. So this quantum theory, whatever theory we develop to explain this electrons interfering, it must explain the individual electrons that are appearing as a localized spot. So when I have only a few electrons, like in panel A here, I'm seeing only localized spots. So it should explain that, as well as it should explain panel D, where I'm seeing an interference pattern. So we need some sort of a state descriptor and some sort of rules that we can use to extract measurable predictions. Because when I make a theory, right, I could make up a theory like there is an invisible man next to me, but there is no way to prove it or disprove it, right? So it's not really a theory. So I need some rules that can extract measurable predictions from it. And so we introduce the concept of a state or wave function. And bear in mind that this is only a mathematical tool, right? So what we observe is experimentally is the pattern that you see here. And to explain that, we are using a mathematical tool. So the wave function that we are going to introduce, this itself is not a measurable or an observable property. It is something that is a mathematical tool that helps us establish this quantum theory. So that said, so when both slits are open, we see that it is showing interference. So we can do analogy with, for example, light waves. So in light waves, as you know, light is an electromagnetic wave, meaning it has oscillating electric and magnetic fields. And so if I denote the electric field as E, if I denote the electric field of light as E, right? And then we can say that the intensity of light, I, is proportional to E square. That is electric field square, right? So there is some sort of electric field like wave function. Of course, electric field is something very physical, but the wave function is a mathematical tool that is interfering, just like how the electric field interferes in case of electromagnetic waves. So the quantum lesson is that the object that interferes is the probability amplitude. That is the wave function psi, which we are going to talk about in more detail. This is encoded by that wave function. So as I said in the previous slide, our theory, quantum theory that we are developing, should explain both these individual particles that we are seeing in panel A. That is, when each particle, when I'm looking at a single particle, a single emission from the source, it appears like a localized shot on the screen. But when I collect multiple particles, then I see the interference pattern, which is in panel D. So our theory should explain both of these. That is, how it is behaving like a particle with a localized detection versus how a pattern is emerging after how a pattern is emerging after we have multiple electrons. So I hope you're able to follow. So if you have any questions as we are going through, please use reactions button to raise your hand, and then we can pause and then have any questions. So we're introducing this complex function called psi, and so we have two slits. So we have slit 1, let us say, and then we have slit 2. And so if we have psi 1 for slit 1, that is the particles coming from slit 1, and psi 2 for this thing, then when we do the amplitude square, that is psi 1 plus psi 2 squared, then we would get, based on the coherence, we would get based on their how they are, we would get basically this extra term 2 psi 1 psi 2, right? So it is not equal to just psi 1 squared plus psi 2 squared, and it is this psi 1 psi 2 term that actually leads to the interference pattern, the ensemble patterns that we see. So if we have an individual particle, it is going to appear like just a single shot, but if we have both slits, then we see this the interference pattern. So the psi, the state function that we are going to talk about, is it has all the accessible statistical information. So if you do not have background in quantum mechanics and you are not able to understand what we are talking about here, please hang on, and we will discuss this in more detail as we proceed in the course. So now we have established that there are some experiments that are showing results which cannot be explained by quantum mechanics. So we are going to begin explained by classical theories. So we are beginning to develop intuitively by looking at the experiments. We are beginning to develop this quantum theory. So we are putting ourselves in the shoes of those scientists back then in early 1900s who saw these really new results that cannot be explained by classical physics, and we want to explain these results in terms of a new theory that we are building up. So we come up with the first postulate, which is the state postulate, where we are saying that any microscopic system, like the electrons that are being emitted from the filament or the source in the Hitachi experiment, or the electrons in the Davison-Germer experiment, or the mercury vapor where we observed discrete energy levels, these are prepared under specified conditions, and the state is basically defined by how the system is prepared, right? So the preparation procedure defines the state or the wave function. So identically prepared systems form an ensemble of systems that are labeled by the same wave function. So when we talk about ensembles, we often think about a multi-particle ensemble, meaning that I have multiple particles that are different from each other, and that is what I would consider as an ensemble. For example, if I want to measure the average height of the participants in this Zoom lecture, then I would need to measure the height of each individual, and then I can take the average. And each individual is different from the other. And so what we have is a multi-particle, multi-individual ensemble. So here, when we say ensemble, it is not a multi-particle ensemble that we are talking about. We're talking about a single particle ensemble, meaning we are preparing the same electron. For example, in the Hitachi double slit experiment, every time it is an electron. And every time that electron is coming from the same source at the same voltage, and it is being prepared the same way. And so these are identically prepared single particle ensembles, which are very different from a beam of particles or multiple individuals, like how I mentioned. And it is this ensemble that we are labeling as the state function or the wave function, which is same as psi. So that is the first postulate. And this is called the ensemble interpretation. There are multiple interpretations of quantum mechanics. The standard interpretation that is often used is Copenhagen interpretation, which is not very physical. And we will see why that is in later slides. So we're going to focus on ensemble interpretation, where we're considering single particle ensembles in this course. So quantum mechanics is inherently a statistical theory. It is not predicting the outcome of individual measurement. It only predicts statistical outcomes of ensemble measurements. So an ensemble again is identically prepared system, a single particle ensemble that is different from multi-particle ensemble. These are not different individuals. These are a repetition of the same experiment on the same individual, right? So these are identically prepared single particle ensembles, right? So when I say beams of particles, these are not beams of multiple particles, but each electron going by one, right? And they're identically prepared. So we're measuring on identically prepared states. So when we talk about state, the state is giving us information to compute statistics. So whenever we talk about statistics, it's not a single measurement. So I cannot measure a single electron and say this is, I found its state. So the state is not really a property like how momentum is a property of a single electron in classical physics. So it has information regarding statistical outcomes of an experiment. In classical mechanics, we say there are trajectories. That is to say, for example, if I were to throw a ball, right? Let's say I have a ball. Let's say I throw it up with some, I give it some momentum, right? I throw it up. And so I know that, this ball is, let's say, on Earth. So it's going to be attracted by the gravity, right? So as the ball goes up, right, it's going to go up, right? And then fall somewhere, right? So this is a trajectory that I can map out, that is using, for example, simple Newton's laws. And if I know the initial velocity, which direction it is, and the initial position, then I can track where the ball is going to go, at what time it will reach the maximum height, and at what time it will touch the ground again, and how far it will be from the initial position. So that is classical mechanics, where we have completely deterministic, completely predictable trajectories. So here in quantum mechanics, we don't talk about trajectories, because we are not talking about a state of an individual particle. The state here is not momentum and position like in classical mechanics. The state here is referring to ensemble measurements. So that is something to be noted, that there are no trajectories here. So what we are going to do is, we said after looking at the Hitachi double slit experiment, we saw that there is some sort of wave structure that is associated with each particle. So we want to now mathematize this from what we are observing. So we look at what is a wave, right? A wave, we can represent a wave as e to the power ikx, right? This is a single plane wave, e to the power ikx. So if you look at that, right, e to the power ikx, right, that would be cosine kx, right, plus I sine kx. Right? So it does not die down anywhere. It is not going to die down. It's oscillating everywhere. It is not localized. It from minus infinity to plus infinity, right? So it is going to keep oscillating. So that is a single plane wave that is spread everywhere. It has a definite momentum. Here by momentum we mean this k related to this wave vector k. And we will look at this de Broglie relation, P is equal to h bar k, towards the end of the second lecture or the first lecture, based on how it goes. But it is not localized. That is, we know the momentum of this, but this plane wave is extended from minus infinity to plus infinity. So it is everywhere. But if I want to model a localized particle, why do I want to model a localized particle? Recall that when we look at the Hitachi experiment, when each electron is coming, I see a localized spot on the detector. The wave pattern, the interference pattern builds up only after I have multiple electrons. So whatever theory we are developing, it should explain the individual particle as well as the interference pattern. So first I want to start with explaining the localized particle. So to model a localized particle, obviously I cannot use a single k. The reason is, if I use a single k, the wave that is associated with a single k is e to the power ikx, which is spread out from minus infinity to plus infinity, right? So what we use is, we use Fourier synthesis. That is, we combine multiple momenta to localize the particle. So this is how we could do it using Fourier transform. That is, I am taking different k. I'm taking different k values, as you can see here. So this e to the power ikx, the k ranges from minus infinity to plus infinity. So I'm taking multiple k values. For each k value, I'm assigning some sort of a weightage, which is given by this phi of k, right? For example, this phi of k could be 1. If it is a single momentum, right, then it would be a direct delta function, right? If it is a spread of momentum, like we could say it is a Gaussian or whatever distribution, right? And we can combine these to build a wave packet. For example, here you see that I take multiple, if I take some momenta here, right? If I take some momenta here, as you see, I can use those momenta to build a Gaussian wave packet. So this is to say that the waves that I'm using are being combined to model the particle that is extended from minus 2 to plus 2, right? If I take only single momentum, then then it is spread. It is completely delocalized from negative infinity to positive infinity. So I do have a better way to visualize this on upcoming slides. So we say that this phi of k is the momentum space distribution, and so whenever you have a broad momentum distribution, you would have a sharp, narrow position distribution, and whenever you have a broad position distribution, you would have a sharp momentum distribution. So for example, if you have single k, then you have almost infinite delta x. If you have other way around, it goes the other way around. So I have a code here to visualize that. So let me stop this, and then I am going to share the code. So during this, we will be using Google Colab. So if you are not familiar with Google Colab, you can go to your Google Drive and you can create a new collab, and we will discuss that more tomorrow. We have a basic introduction to Google Colab and NumPy, and we will use Qiskit, which we are going to where we are going to do quantum circuits and quantum algorithms later in the course in week 2, also in Colab. Of course, you can do this also locally on your machine, but we will be sharing these Google Colab files with you, which you can download as Python notebooks, and you can use them locally on your machine. So here I have, you can see that if I use a narrow range of k, right, you see that the position is spread out from minus infinity to plus infinity. And if I use moderate range of k's, it will be going from minus 20 to plus 20, but you see a small peak here. If I use a wide range of case, then now you can see that I can model a localized particle here. So we will share these codes and you can play around with these codes. The only thing that I would request is do not edit the code that we share here. You can make a copy. So you can go to file here and you can make a copy, save a copy in your own drive and edit that code. Because if you edit here, then it will be problematic. So please save a copy in your own drive and edit that, or you can download the notebook and you can download it as a Python notebook and you can edit on locally on your machine. So you can play around with this code. So here I have created multiple sets of k values. So we will see this NumPy. If you know NumPy, that is great. If you do not know NumPy, we do have a basic introduction to NumPy tomorrow, and you will get more familiarity with that then. So I have just put a different range. So you can reduce this range if you want. So for example, I can make this to like 0.05 to, let's say, plus 0.05, and let's say we make this to let's leave this as 1, and let's say this is 6, right? And then let's run it and see. So you see that this wide range, wherever I have the wide range, the wave particle is localized because I'm using multiple momenta to build the wave packet, right? So I can use this multiple momenta to build the wave packet. So there are multiple waves that are giving me a localized spot. This can explain the panel A that we saw in the Hitachi experiment, if you recall. So in Hitachi experiment, we were seeing single electrons that were appearing on the detector as a localized particle. So then I could use this wave structure, this kind of a Fourier synthesis, to explain the localized detections on the screen. But at the same time, this is being built with multiple waves, multiple Ks. So when I have multiple particles that are going in, that is, I repeat this experiment for several electrons, then I would see the interference pattern build up, because there is inherently, whatever the localized particle is, inherently is associated with this kind of a wave structure, how we are building these wave packets. That's the drive home message here. So you can play around with this code and see, learn more about how this wave packets can be built. So let me go back to the okay. So that's what we have just seen, that we can build these structures. So the code link is here, and we will also share these notes with you. So now what we want to look at is how does this Gaussian wave packet evolve with time. That is, let's say I have a particle. So in the Hitachi experiment, clearly the source is here, the detector is here, far from the source. Let's say the source is on the left and the detector is on the right, and the particle must move from the source at time t is equal to 0. Let's say it is emitted, and then it is going to travel to the detector. So there is some time lapse between the source and the detection. So if we model the initial particle as a Gaussian packet like this, so like how you see here, like a Gaussian packet in blue that I'm showing here as a localized Gaussian packet, if I model it like that at time t is equal to 0, what we want to look at then is how is it going to move as the time proceeds, right? So we want to look at the evolution of this Gaussian wave packet. So this is where we are developing quantum theory. So our goal here is to explain the interference pattern and the localized particles that we observed. So to explain the localized particles, what we said is that it is associated with a wave structure, and these different wave structures, I can combine different momenta, different e to the power ikx with given weights that are denoted by phi k, and I can build a localized particle. So that explains the localized detections. But now we want to explain the interference pattern. So we need to see how this evolves in time. So we want to look at the time evolution of these packets. So we begin with something called the Schrodinger wave equation. So the Schrodinger wave equation is like a diffusion equation. It's not a diffusion equation as such from the classical sense, but it is like a diffusion equation that is telling us how this free particle, that is how this Gaussian wave packet that is at time t is equal to 0 evolves in time, right? So on the left hand side, you see a time dependent derivative. The psi is denoting the state function or the wave function, the state. Again, the psi is not for it is not the property of a single particle. It is denoting an ensemble of similarly prepared systems. And on the right hand side, it has to do with something with space. The del square is a spatial derivative. So this is a time dependent Schrodinger equation which we are going to use to see how the Gaussian wave packet is going to evolve in time as the particle moves from the source to the detector. So first we begin with a free particle. A free particle means it is not interacting with anything. So this is a conceptual thing. Really there is no free particle, because when we say there is something, it must exist only in relation to other things. So it must interact with everything else. So whatever we are saying that there are no external forces, it is, we are conceptually turning off all the other interactions, right? So we are looking at a free particle that is not interacting with anything else. And so if we can describe this free particle that is at one spot as a Gaussian wave packet which is combined with multiple plane waves like how we have seen in Fourier synthesis, so we write that state as e to the power ikr. This is the thing that we have seen, e to the power ikr, right? That is plane wave, right? That is spread all over, and so it has a single momentum, and then omega t is what is the time dependent thing. So from here we get energy of the particle as h cross omega or h cross square k square by 2m. This is the dispersion relation, which we will discuss when we discuss de Broglie relation, how this comes about. But it mainly comes about from this part, the left hand side of the Schrodinger wave equation, where we are taking the time derivative, right? So you see one imaginary part here in e to the power I, and then when you do the time derivative, you get a negative w, right? So when you do dou psi by dou t on this, right, you get negative iw, right? And then when that is multiplied with ih bar, you get h bar omega. So this is related to the energy of the particle, and that is what we're going to talk about in terms of de Broglie relationship later. But primarily here we are expressing a single free particle which we are conceptually thinking about, that is not interacting with anything else, as a combination, as a single plane wave, but we can combine these plane waves to make a localized wave packet. Now the next question that we have is, but really every particle is not really free, that is, it is interacting with surroundings, or it is present in some electromagnetic field or in some sort of a particular situation. And so then we include that particular situation, the forces that are acting on it or the external fields that it is present in, right, as a potential V of RT that you see here. So for a free particle, we set this V of RT to be 0. But in general, like I expressed, there is no really a free particle. So you have whatever external 0-point field or whatever field. If it is in a harmonic oscillator, you have this potential. If it is in a hydrogen atom, you have the Coulomb potential, right? So different types of potential based on the physical situation of the particle. But ultimately, what I want you to the take home message here is that we can model a particle as a combination of different plane waves using Fourier synthesis, and these wave packets can evolve in time based on their interactions with the surroundings, which are encoded in the potential V, according to the time-dependent Schrodinger wave equation. So this is the basis that we are using to explain the results that we observe. Now, given this, we can, using this equation, we can see how these wave packets evolve and how, if we have multiple wave packets, how these interference patterns or discreteness or diffraction can emerge from these, right? So we're simply trying to build this quantum theory here. So the time-dependent Schrodinger equation for free particle, we can see how that would evolve in time, right? And so we can actually analytically solve this, and we would get an equation like this. So previously, on one of the slides, I had psi of x at t is equal to 0, right when the particle is emitted from the source, right? We were describing it as a wave packet. As time evolves, right, this wave packet is moving, right? So you see there is some time term here, right? That the position is changing. So there are time terms here. That is, we are getting the solution from here, from the time-dependent Schrodinger wave equation, right? So let us visualize how this looks. So basically, what this means is that as the particle is moving, it may have a certain set of momenta that describe it when it is emitted right from the tip. That is, to make the wave packet right after it is emitted from the tip, we use a certain set of momenta. But as the particle is evolving in time, it is going to expand. The number of momenta that we have to use is going to increase. So it's going to spread out. The width is going to grow, and it is going to keep moving. So let's see, we can use this Schrodinger wave equation, and we can actually compute how this wave packet is evolving. So let me show that to you on the code that we have. So it is the same Colab notebook. So you can see the first part was making the wave function itself, and then the second part is this is showing the motion of a free Gaussian wave packet. So first we are building what a Gaussian wave packet is. So just like how I described, and then we are just basically looking at multiple Gaussian wave packets. So you can run it, and I already ran that, and I have the output here. So I'm going to just simply open the output instead of running it, but you can copy the code and run it. Okay, please zoom in a little bit. Okay, so okay, I will zoom in a little bit. Okay, I hope you're able to see this better. So this is the wave packet. It is beginning with, so we built this wave packet. So it is beginning with a width, right? You can see the width here. So this is at time t is equal to 0, right? And then we use Schrodinger wave equation to see how this is going to evolve in time. So as it evolves in time, we would see that it is broadening. That is, I have to use more momenta. So here you see that the particle is spread from along x-axis. It is spread in, it has some extension. So whatever physical thing you can think of, whatever physical particle you can think of, the basic thing is it must have some extension. It must have some like width, right? Even the electron, even if you think about whatever, however small it may be, it must have some extension, and based on that extension, I have to use different sets of momenta to build that wave packet. And that's what we have done here. We're taking some hypothetical particle and we have built some wave packet at time t is equal to 0, and then we are applying Schrodinger wave equation to see how that evolves in time. And so as you can see here now, as the time evolves, the particle is moving and the width is increasing, right? You see that it is spreading out, right? So let me replay that again. So as the particle is moving, you see the width is increasing, right? That is, I have to use more momenta to describe the wave packet, right? Or less momenta to describe the wave packet, and more positions where the particle could be found. So I have to, sorry, I take that back. I made a mistake here. So in the beginning, you need less momenta because the particle is, you need less positions and more momenta as the particle is localized. But as the particle is spreading out, if it is fully spread out from minus infinity to plus infinity, then we need only one momentum to describe that. And that is what is happening. So as I let it go, it is spreading out. The wave packet spreads out. And this we are getting from the Schrodinger wave equation. So the Schrodinger wave equation essentially is telling us how this evolves. So for example, if this is for a free particle, but if it is in some potential, then we will see that there are differences how it changes based on the potentials. So let me stop this, and then let's go back to our presentation. Okay, Priyanshu is asking a question, that is the Schrodinger wave equation some sort of trajectory of the wave function? So very good question, Priyanshu. Thank you for asking that. So remember that when we talk about trajectory in classical mechanics, we're talking about a single particle, right? And we are talking about how that single particle moves. But here the wave function itself is a conceptual mathematical tool we are building for an ensemble. So it is not really, the wave function itself is not a single particle. It is an ensemble that can predict only statistical outcomes. So it does, in a sense, tell you how this statistical ensemble is moving. Like for example, as we have seen in the Gaussian wave packet, the initial wave packet itself is made up of so many different momenta, and how that evolves as time goes by, you can sort of see that how the momentum distribution is changing, but it is not similar to classical mechanics, right? Okay, so then what about the system that is described by the phase space? So that's what I was saying, that it is, that we can look at it as ensemble. If you want to look at it as a trajectory, it is, you can think of it, if you want, as a trajectory of the ensemble that is associated with the particle, but rather than deterministic single particle trajectory like in classical mechanics. I hope that answers your question. Okay, good. So this is what we have seen so far for the free particle. We have seen the experiments, we have built this free particle wave packet, and we saw how it is evolving in time and how it drifts in time. It is spreading out, right? And we saw the code. So single detections are localized hits, like the wave packet that we built, and patterns emerge over multiple trials. So we were able to explain so far in whatever theory that we are developing, we can explain only single detections, because we saw that this wave packet can be built. We have not yet really explained how patterns emerge over many trials. So for that, we have to come up with a new postulate. Remember that we started with one postulate. The postulate is that based on how we are preparing the particle, right, I can assign a state to this preparation procedure, and I have to look at multiple particles, that is the same particle, identically prepared particles, multiple of them, like multiple electrons that are not coming at once but one by one, but it is prepared the same way. I have to look at collect so many electrons to see the interference patterns. Each individual electron is appearing like a localized hit. That part we are able to explain, but we have to still explain how the pattern is emerging. So for this, we come up with the second postulate. Before we go to the second postulate, a quick probability refresher is that we can define a probability density function, PDF, right? And we can calculate mean or average, or what we usually call in quantum mechanics expectation values, right? So we can compute the expectation values if we know the probability distribution as p of x. So so x p of x is excuse me, can you open the password? Got locked off. Okay. Okay, perfect. Yeah. So here we see this is the probability density function, and that's how we calculate the mean. And then we are also going to talk a lot about variance, or we are going to talk about delta x or delta p, things like that, which we calculate from those relationships, right? This is just simple classical probability. So now we built this wave function or the state function psi, right? So how do we get this probability density from psi? That's what the second postulate has to do with. So the second postulate is often called the Born postulate, which says that given a state psi, the probability density is given by psi square. So psi, the state in general, could have complex numbers. So when we take psi square, we are using complex conjugate, right? So for example, if I say psi of x, like if I take a single plane wave as e to the power ikx, right, then psi square would be psi star, the complex conjugate, times the original psi, which would be e to the power minus ikx times e to the power ikx, which would give you 1, right? So this psi square would always range from 0 to 1, right? It cannot be negative, it cannot be more than 1. It is giving you some sort of a probability, right? So psi square, we say, is giving you some probability density. It is not a material density. It is not that the same material is spread out. It is giving you the probability density, meaning that there is a probability of finding the electron here in this particular part of the screen versus in this particular part of the screen, right? So these probabilities refer to ensemble frequencies in identically prepared runs. That is, every time I have the source emitting the same electron, and based on these ensemble frequencies, we are building this psi square. So once we have defined this psi square as the probability amplitude, then we can see how patterns emerge. So with postulate 1, we were able to explain these localized hits that we saw in the experiment. And with postulate 2, the Born rule, that is psi square is the probability and that it is normalized to 1, we can explain the interference pattern. So whatever psi we build, we normalize it to ensure that the probability doesn't exceed 1 and it stays between 0 to 1, right? So this normalization procedure, for example, if I build a Gaussian wave packet, so for example, this is the Gaussian wave packet that we built in the beginning. That is, if I draw the psi of x versus x, it would look with something like this, with a width of sigma, right? That is given here, right? Or 2 sigma, that's given here, right? So that's how it would look like, right? So, but we want the psi square to be at max 1. If I integrate over all space, if I integrate from negative infinity to positive infinity, I must be able to find the particle somewhere, right? So then if I integrate from minus infinity to positive infinity, I must be able to find the particle somewhere. So the total probability should be 1. So then we can use standard integrals to normalize and find what should be this multiplying factor A. And that is what is called as normalization. So we say that when we say that we are normalizing the Gaussian, what we are doing is we are ensuring that when we square this wave function, we are assured that the probability is going to fall between 0 and 1, right? Otherwise, it would not be physically meaningful. So that is what this normalization procedure is used for. So once we have normalized this wave packet, right? And we are assured that the probability density is going to be between 0 and 1, right? We can then use let me go back, sorry. So once we have normalized this, then we can recall that we have said that from two slits, if I have from the first slit psi1 and second slit psi2, just like the electric fields, now if I want to find the probability of particles, then I have to find psi1 plus psi2 squared. So when I find psi1 plus psi2 squared, then I get the interference terms, which come up as psi1 squared plus psi2 squared plus psi1 2 psi1 psi2. Right, so this is what is going to, or I should write as the complex conjugate to ensure that the part is real. So this extra term is what is leading to the patterns that emerge. So using the first postulate, we were able to explain individual detections, and using the second postulate that psi square is the probability, we are able to explain the patterns that emerge over time, right? So these are the two main postulates that we will discuss in this lecture. And we are going to take a break in some time. After we come back from the break, what we will discuss is a little more about uncertainty, and then define some uncertainty relations, and talk about more about ensemble and statistical interpretation versus Copenhagen interpretation. And then we would introduce some basic examples of two different potentials, because so far we have discussed only the free particle, which is not interacting with anything, which has no potential. So we are going to then use some cases where there is a potential, like a 1D potential well, which is idealized, or an imaginary scenario in one dimension, and also a harmonic oscillator, and that we will do in the next part after the break. So we will stop the lecture here and see if we have any questions. We have one question. So Priyanshu has another question. He says that the wave function can describe the behaviors shown in A and D not in the Frank-Hertz experiment, in the double slit experiment. Can describe okay, are these two statements contradictory? So these two statements are not contradictory, because we are talking again about the ensemble evolution itself. That's why I said you can think about it like the ensemble evolution, and it is not, we do not know exactly, like for example from the source, when the electron is emitted, I do not know exactly its momentum, I do not know exactly where it is emitted, when it is emitted, so I cannot really track the trajectory. This is a conceptual ensemble that we are using to build this, and we are not looking at the pictures A and D in the Frank-Hertz experiment, but rather we are looking at the Hitachi double slit experiment. So we will not be able to describe, even using Schrodinger equation, although you can think about it as if it is doing for single particle, it's a statistical outcome. That is, after I have accumulated multiple particles, only then I can see the interference pattern. I cannot see interference pattern for a single particle. So I'm seeing the interference particle for multiple particles that are accumulated. So it can describe the ensemble, not a single particle trajectory. So I hope that answers. Okay. So we have a message from Dr. Gargi, that is, please join on time by 4:45. And if you have any questions, please feel free to leave them in chat, or if you want to ask them, I welcome you to ask them when we begin the next lecture. And before we begin the next lecture, we will do the same quiz again to see if your understanding has changed, or if this added any value to your understanding, to track that objectively. And so we will take a 30-minute break and join back here at the same Zoom link at 4:45. Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.
And also, please feel free to leave comments about whether you are understanding this, or whether, whatever you have, you can leave comments, and I assure you that your comments will not be reflected badly in receiving the course completion certificate. I want to make sure that we are covering the basics that are needed. If you based on your familiarity with the course material. So please do feel free to leave comments in the chat box. We're going to leave the Zoom on. We will join back here at 4:45. Thank you.